everyone, let's talk about mass spectrometry and average atomic mass. We've already seen that Dalton's assumptions about atoms were incomplete. He just didn't know the whole story. The evidence for negatively charged particles and positively charged particles we've already seen had already shown us that atoms were not indivisible, and that was his first idea, or part of his first idea. But there was more. As scientists continued to experiment with cathode ray tubes and electricity, something curious was found when they were working with neon gas. There seemed to be two different weights of neon, even though all of the atoms behaved the same chemically in all the other ways, but there just seemed to be two different weights. And so this idea that we have two different masses for neon is actually going to allow us or force us to revisit Dalton's second idea. His second idea said that all atoms of a particular element are identical to each other and different from all other atoms of other elements. Well, apparently, all the atoms of one element are not actually identical. So let's take a closer look at this. The current technology we have to investigate the mass of atoms is called mass spectrometry. We aren't going to go into details as to how the instrument works. If you're curious, ask me. I'm happy to chat about it. But basically, it's a tool that sorts atoms and particles by their weight and tells us how many of each weight of particle there are in a sample. The output of a mass spectrometer is a graph that looks like the one below. The x-axis is labeled m/z, and this stands for the mass-to-charge ratio of the particles. Mass to charge ratio. In effect, this is the mass of the particles because of the way we're using the instrument. As we're talking about individual atoms here, using the unit of grams is inconvenient because they're so tiny. Instead, we're going to use atomic mass units, which is abbreviated AMU. Now, these units were carefully designed so that the mass in AMU of a single atom is the same as the mass in grams of 1 mole of that atom. So if I have a nitrogen atom that weighs 14.08 AMUs, 1 mole of those atoms would weigh 14.08 grams. It's really nice because this means those mass numbers on the periodic table still work for us. It's in grams if we're talking about a mole, or AMU if we're talking about individual atoms. The y-axis is percent abundance. So what percent of a sample in the particle have a given mass? These should add up to 100% as percents do. So when we look at a mass spectrum for an element, it tells us how many different kinds of atoms there are. So how many different masses there are of this particular element. And then what those masses are and their relative abundance. If we look at the mass spectrum on this screen, we see that there are two different types of atoms in this sample. One kind with a mass of 10 AMUs and a second with a mass of 11 AMUs. And that we have more of the 11 AMU type of this atom than we do that of the 10 AMUs, because we see that the bar for the 11 AMU type has a percent abundance of around 80%, while the 10 AMU type is only around 20%. Each of these types of atoms is called an isotope. An isotope is an element with a particular mass. Some elements have only a single isotope. All their atoms weigh the same, while others have many, 5, 10, 15 different isotopes. Either way, when we talk about an isotope of an element, we mean all of the atoms of that element that have a particular mass, that are identical to one another. The question has to be begged as to what causes the difference in mass of these different isotopes. Early scientists hypothesized there must be a third subatomic particle responsible for this, to go along with the proton and electron. There must be something else. And that it must be neutral in charge because they couldn't locate it using electricity, just like they had for the proton and for the electron. Now, it took a lot of years and some really careful experimentation to confirm that this particle actually existed. But in 1932, James Chadwick was able to detect the neutron itself. And that's what this missing neutral particle is, our neutron. The neutron is found in the nucleus of an atom with the protons, and it has very nearly the same mass as a proton does. And so different isotopes of a particular element have different numbers of these neutrons, and this results in different masses for the atom as a whole. We can look at a mass spectrum to determine how many isotopes a particular element has, and to estimate the average atomic mass for that element. When I talk about the average atomic mass, I'm talking about if I were to take a scoop of, say, a mole or a half a mole, but like lots of particles, on average, how much would those particles weigh? Because there are different amounts of each isotope, we do have to take what's called a weighted average, the average value that takes into account the relative amounts of those different isotopes that are present. In this case, because I have more of the isotope with a mass of 11 AMUs, my average mass is going to be closer to 11 than it is to 10. Maybe, here-ish. And so maybe I want to estimate that to be, say, 10.8 or so. The mass number we see on the periodic table is this average atomic mass, because realistically, how often do we work with a single atom? Almost never. We always have a big collection of them. And so when you look at those mass numbers, they're not whole numbers, they're decimals. And the primary reason those numbers for the mass are decimals is because they are an average of the different isotopes that are present for a given element. Let's look at a second mass spectrum. How many different isotopes do you see here? If you said 5, you're right. 1, 2, 3, 4, 5. 5 different peaks or different bars on the graph, each one indicating an isotope. If we think about where we would expect the average mass to fall, it should be closer to 58 than to 64, because there is substantially more of the lower mass isotopes than there are of the higher mass isotopes. Maybe, 59-ish. If we look at the periodic table, we see that nickel has an average atomic mass of 58.69 AMUs. And so that's going to be pretty close to what this is. Oh, and yeah, that is this element. This is nickel with its 5 common isotopes. And so we can estimate average atomic mass by looking at both the masses and the relative abundance. And your average mass should be closer to the higher abundance higher abundance isotopes, excuse me. And while estimating average atomic mass is fine, it'd be much more satisfying if we could actually just calculate a more accurate number for average atomic mass. And so we need an equation. In order to calculate the average atomic mass, we multiply the abundance in decimal form by the mass of an isotope, and then we add that to the abundance in decimal form times the mass of every other isotope we have in a sample or for a particular element. So for example, here, if I have only 2 isotopes, I take the abundance in decimal form, so take your percentage, divide by 100, multiply that by the mass, add that to the next isotope's abundance times the mass. If I had a third isotope, I'd have abundance times mass again. Just add them all up. And this works regardless of how many isotopes there are. You just keep adding the product of the abundance and mass for as many isotopes as you have. An example, so you see how this works. We're going to calculate the average atomic mass of gallium, and it only has 2 common isotopes. So there's one isotope which has a percentage of 60.11%, and that one weighs 68.9255 AMUs. And then the second one is 39.89%, and that weighs 79.247 AMUs. So I will take the percent abundance and divide by 100, so it's in decimal form, and multiply that by the mass of that isotope. And then I will add that to the second isotope's abundance times mass. And since I only have 2 isotopes, I can stop there and add these up, and you get 69.72 AMUs as the average atomic mass. If I had a mole of these, it'd be 69.72 grams for that average atomic mass, which, if you look on the periodic table, matches for gallium. So in summary, it turns out that all atoms of a particular element are not necessarily identical. An element can have multiple isotopes, atoms with different masses that are the same element, due to having different numbers of neutrons. We can use mass spectrometry to determine how many isotopes an element has and estimate the average atomic mass. The average atomic mass can also be calculated rather than estimated if percent abundances and masses for the isotope of an element are known.